In the last lecture, we saw two ways of thinking about what work is and how to calculate it. We said that it's equal to the amount of energy transformed by that force. So in other words, if we have some object that moves some distance while a force acts upon it, then that force does work. And if that force is somehow connected with some form of energy being transformed into another, so I've called it E whatever, right? Some sort of energy, I don't care what, and we transform an amount delta E of it into something else, like say kinetic energy, then the work done by that force is equal to delta E, where I'm using absolute values here because there are some signs that we should worry about, but we're not worrying about them yet. And the other way of thinking about it is that the work done by a force is just the force times the displacement. However, if you think about it, this can't be the full picture. And here's a simple example to show why. If you carry an object in your hand at constant speed, maintaining it at a constant height, so it's moving at a constant velocity, and so we know that the net force on it is zero. The only forces acting upon it will be a normal force up due to your hand and a downward force, the weight, due to the earth. Well, it's moving at constant speed, so its kinetic energy is constant. And it's moving at constant height, so its gravitational potential energy is constant. So we have to conclude that no work is being done on this object because its energy is remaining totally constant and no energy is being transformed from one form into another. But there are two forces acting on it, and it's going through a displacement. So why is it that the normal force and the weight are doing no work in this case? You might be tempted to say, well, maybe what we need to think about is the net force, and maybe there's no work being done because the net force is zero. But that can't be right either, because think instead about raising an object at a constant velocity with your hand. So now, again, its kinetic energy is constant because you're raising it with a constant speed, but it's going up. And so its gravitational potential energy is increasing. But again, it's not accelerating, so the net force is zero. So this object definitely does have work being done on it, but it's got the same forces acting on it as the previous example, and the net force is still zero. So clearly there's something more we have to understand here. Why is it that in the one case the normal force and the weight do no work, apparently, because no transformation of energy is taking place, whereas in this case clearly some force is doing work because this object is increasing its gravitational potential energy? In the last lecture we looked at this case with a rocket car going down the runway, and we knew the thrust due to the rocket engine, and we knew the mass of the rocket car, and we knew how far it was going. And we found that the work done by the thrust, so the work done by the thrust was just that thrust times r delta x. And if we set that equal to the change in kinetic energy, which was just, it started at rest, so that was the final kinetic energy, so just a half mvf squared, we were able to solve and get 184 meters per second, which was correct. Now, to try and figure out what's going on here, let's see what happens when we change the direction of the thrust. So now the thrust is going to be directed at an angle 60 degrees down. Now, if the work was just as simple as what we did here, then we would expect to come up with the same answer, the same amount of work done, and so the same final speed. But I think you probably have a sense that changing this angle is going to change the final speed. Before going on and having a look at this, though, let me just point something out. I didn't pick 60 degrees arbitrarily. Now, you may or may not know it, but the cos of 60 degrees is a half. And so what that tells us is that the horizontal component of this thrust is half of the magnitude of the thrust. And so what we're looking for is a factor of 2 somewhere. And maybe you think that what's going to happen is that the final speed is going to be a half of what we came up with here. We'll see. Here's our modified rocket car with the rocket engine at a 60-degree angle, and we'll light it up, and off it goes down the runway. And I've just skipped ahead to the point where the little guy standing a kilometer down the runway is in the background here, and we can see that it's going at 130.3 meters per second this time. So let's see what we've got. This time we had a final speed of 130 meters per second. Now, if you thought we were going to have half of the final speed that we had before, you see that's not true. Half of 184 would have been 92. So apparently it's not the speed that gets divided by 2. So what is getting divided by 2? Well, look that there's an ft here. What if that's supposed to be the horizontal component of ft? So in that case, we would have that our work done by ft would be ft cos 60 degrees times delta x. And if we let that equal our final kinetic energy, now we get that comes out to 130 meters per second, which is a match for what we saw. So here's the key. The part of the force that does work is the component that's in the direction of motion. And so we can now update our definition of work. The work done by a force is the force times the displacement, these are magnitudes, times the cosine of an angle, where that is an angle between the displacement vector and the force vector. Let's return to this case of carrying an object along at a constant height at a constant speed. So let's ask how much work the normal force does, because this was our problem before, that our work formula told us that it should be doing work, but we could see clearly that no work was being done. Well, the normal force is up, and the displacement vector is to the right, like that. And theta, as always, is defined as the angle between them. And our new work formula tells us this, that the work is the magnitude of the normal force times the magnitude of the displacement times the cosine of the angle between them. And we usually just write it like this, right? No vector symbols on those, so these are talking about magnitudes. But notice that if the normal force is straight up and the displacement vector is to the right, then that's a right angle. And cosine of 90 degrees, you may or may not realize this, is 0. So that tells us right there that the normal force is doing no work. And in fact, any force that's perpendicular to the direction of motion will do no work. So in this case, you can see the weight is also perpendicular to the displacement, and so the weight is also doing no work. Let's use what we now know about forces perpendicular to the motion doing no work to analyze a situation that we would have a real tough time with if we were to do it using Newton's second law. So here's a roller coaster, and as the roller coaster car goes down the hill, it's going to speed up. And the reason this would be so difficult with Newton's second law is, if you think about it, at any time on the hill, the free body diagram is going to look like this, with a weight and a normal force. And the thing is that the normal force is changing direction all the time, and so is F net. It's always the component of the weight parallel to the slope that is speeding the cart up. But how large that component is changing because the angle is changing all the way down. And so this is a non-uniform acceleration, and if we were to do it doing Newton's laws, we would have some trouble. But now let's think about it using energy. So I'm going to start with an energy bar chart. And you know what's happening here. It's going down, so this cart is losing gravitational potential energy. So I'm going to set my axes down here. And looking ahead, that means I'm defining my final gravitational potential energy to be 0. But then there's this normal force. Do we need to worry about this normal force? Well, remember, a force only causes transformations of energy if it does work. And this normal force everywhere is perpendicular to the direction of motion. And so the normal force does no work anywhere on the track, and so we can just totally ignore it. All we have going on here is that we start off, the cart is moving initially, so it has some kinetic energy, and it's up high, and I've defined my axes down here, so it has some gravitational potential energy. And at the end, it has no gravitational potential energy, but lots of kinetic energy. And so there's the energy bar chart. And so I can write my conservation of energy, which I can rewrite like so. And conveniently, the mass is going to cancel out. That tells us that the speed that a cart goes at the bottom is independent of the mass of the cart or the mass of the riders. That's a useful thing to realize. And what we want is VF, so we'll just solve for VF. And we get a final speed here of about 24.6 meters per second. So just look back and notice how simple conservation of energy makes a situation like this. We don't need to worry about the shape of the track. We could change the shape of the track, right? The track could do something weird like this, but as long as the total change in height doesn't change, the speed here won't change. Conservation of energy tells us that, which would be very difficult to show using Newton's second law.